When training a standard linear regression model, the math only has one objective: catch every single data point. But when the data gets complicated, trying to catch every flying particle causes the whole system to break down. To fix this, we look to the regression category of our machine learning map, specifically algorithm number 26, Ridge and Lasso Regression. Standard ordinary least squares regression is desperate. It calculates the exact path through the training data to minimize the distance to every single point, even if that data is full of random noise. The blue line memorizes the data, contorting to hit the red dots exactly, while the green line sweeps a smooth trajectory. This is the bias variance trade-off. The blue curve has zero bias, but massive variance between points. Predicting the future with this will fail wildly. Perfect training accuracy almost always guarantees real-world failure. To make our model better at predicting the unknown, we actually have to force it to be a little worse at memorizing the past. The mathematical fix for this over-eagerness is called regularization. We add a penalty term to the algorithm's loss function. Instead of just minimizing the error, the model is now charged a fee, a tax, for the size of every coefficient it uses. Ridge regression, or L2 regularization, calculates this tax by squaring the coefficients. Large weights get heavily penalized, pushing the math to shrink them down. Lasso regression, or L1 regularization, taxes the absolute value of the coefficients instead. It is a seemingly minor algebraic tweak, but the outcome is completely different. Ridge shrinks all the coefficients smoothly, but it keeps every single one of them active. Lasso shrinks the coefficients, but it forces some of them entirely to zero. Why would swapping a squared penalty for an absolute value penalty physically force the math to drop features entirely? The answer is geometry. That algebra creates a literal physical constraint that dictates exactly how the algorithm is allowed to consume data. This graphic shows the geometric mechanics of both algorithms side by side. The mathematical penalty acts as a physical boundary, a strict budget, that the expanding elliptical regression error contours are not allowed to cross. Look at the left panel. Squaring the coefficients creates a budget shaped like a perfectly smooth circle. Because that circle has no hard edges, the growing error contours will almost always expand until they touch the boundary along a curve. At this intersection point, both the W1 and W2 coefficients shrink, but neither drops exactly to zero. Now shift to the right panel. Taxing the absolute values creates a budget shaped like a rigid diamond, with sharp corners pointing directly along the axes. When the orange error contours expand to meet this shape, the highest probability is that they will hit the diamond directly on one of its projecting points. Because those corners sit perfectly on the axis lines, touching a corner has an absolute mathematical consequence. The value on the other axis is driven precisely to zero. Lasso doesn't perform automatic feature selection by magic. It drops variables because a diamond has sharp corners, and those corners sit directly on a zero axis. This chart compares how 3 different regression models handle a scenario evaluating 6 features, where only 3 contain actual signal, and the rest are just junk noise. The standard ordinary least squares model, shown in gray on the left, blindly assigns value to everything. It lets the noise leak directly into the math, creating a brittle prediction. The ridge penalty in the middle tames the model. It shrinks all the bars down to improve stability. But look closely. None of the bars for the junk features are actually gone. Then we see Lasso on the right. Because of that sharp diamond geometry, Lasso perfectly zeroes out the junk. It recovers the true, sparse underlying model automatically. Regularization is simply least squares on a leash, and the physical shape of that leash dictates whether irrelevant information merely shrinks or disappears completely. Putting this geometric behavior to work on your own datasets doesn't require a master's degree in calculus. You can toggle between these two realities by changing exactly one word of code in a Python notebook. We've covered the math behind Ridge and Lasso regression. To actually run these algorithms, we're pulling the source code straight from the 50 Algorithms linear regression repository. You'll need the Ridge and Lasso modules from scikit-learn. But right next to them is the scalar module, the most critical prerequisite tool for this process. Here are the core execution pipelines for both models, side by side. The syntax is identical. You simply swap out the word ridge for lasso to shift from an L2 penalty to an L1 penalty. This diagram shows what that single word change does to the math. Inside those parentheses is the alpha parameter. This value controls the strictness of that mathematical budget. Set alpha to 0 and you get plain ordinary least squares regression. Dial the number up and the budget region tightens, mechanically shrinking your coefficients closer to 0. While the syntax is brief, the model's accuracy depends entirely on tuning this alpha dial to match the noise levels in your specific data. You should rarely hard-code an alpha value. Guessing the exact penalty strength manually often forces a model to either overfit noise or underfit the true trend. Instead, pass a list of potential alphas into the built-in cross-validation classes, Ridge CV and Lasso CV. The algorithm sweeps through every option and locks in the penalty that produces the lowest error. Once the model finds that optimal penalty, we extract the .coef attribute. This lets us look inside the algorithm's black box and verify exactly how the math altered the weights. Look at the ridge array. The L2 penalty shrinks all the coefficients smoothly, but they remain non-zero. Every single feature is kept active in the equation. Now look at the lasso output. Because the L1 diamond budget hits the axes directly, the absolute value penalty forces some of these coefficients to exactly 0. By reading these zeros, we confirm what the algorithm just did. Lasso performed automatic feature selection, dictating exactly which variables matter for the prediction and which ones can be dropped entirely. We've implemented feature scaling, cross-validation, and regularized regression using just 3 lines of code. Engineering mastery requires moving beyond syntax to determine which mathematical penalty fits your dataset's structure. You have to look at your specific dataset and decide, does this scenario demand the smooth, inclusive shrinkage of the rich circle or the sparse feature selection of the lasso diamond? When building predictive models, you rarely get to choose your mathematical tools based on personal preference. The strict environment of your data dictates the geometry you deploy. If your dataset contains massive amounts of overlapping variables, often more features than you have trusted historical samples, standard linear regression will overfit the noise and fail. That specific data environment is the trigger where regularization becomes mandatory. Consider genomics. A researcher might have 20,000 gene expressions, but only 50 patient samples. They need to isolate a handful of truly critical genes from a sea of background static. This is the primary environment for lasso regression, an algorithm that mathematically zeroes out the irrelevant variables until only the true signal remains. Conversely, take chemometrics. A chemical spectrum might have thousands of highly correlated wavelengths, and every single one contributes to the final prediction. You cannot just delete them. This is the arena of ridge regression, which tames the variables by shrinking their influence collectively without entirely removing any of them from the equation. In quantitative finance, these exact tools are used to scrape generalizable forecasts from massive, noisy market datasets, stripping away the daily volatility to reveal actual predictive trends. The difference in how these models behave comes down to a specific mathematical mechanism. Both Ridge and Lasso share several operational victories. First and foremost, they actively fight overfitting by adding a strict mathematical budget to the model's overall complexity. They also handle multicollinearity beautifully. When multiple input features overlap and provide redundant information, standard models become erratic and unstable. Regularization forces that math to settle down. Because they remain strictly linear equations under the hood, they train exceptionally fast, and the final models are highly interpretable. You can look at the resulting weights and know exactly how the prediction was calculated. The operational choice is stylistic. Ridge provides stable, closed-form mathematical grace, preserving the entire dataset. Lasso acts as a ruthless editor, performing automatic feature selection for a sparse, easily readable model. This bias-variance trade-off graph, but these algorithms have absolute, non-negotiable limitations. First is the linearity trap. If your underlying data curves severely or relies on complex nested interactions, no amount of regularization will save the model. You must abandon linear mathematics entirely and switch to tree-based algorithms. Second, you are strictly required to standardize all your features before applying any penalty. If you measure one variable in miles and another in inches, the algorithm will penalize the raw numbers, which entirely warps the results. Lasso carries a fatal flaw: instability with highly correlated features. Faced with 10 nearly identical variables, Lasso arbitrarily selects one and kills the rest. If data shifts slightly, the model wildly flips its choice, making the system incredibly fragile. Lasso also has a hard mathematical ceiling. It is structurally incapable of picking more features than there are total data points in your sample. To bypass these flaws, practitioners rely on the elastic net. By blending both the L1 and L2 penalties together, Elastic Net maintains the sparse feature selection of Lasso while using the ridge mechanism to protect groups of correlated features from being randomly deleted. Understanding these exact breaking points prevent catastrophic algorithmic failure in production and justifies why hybrid mathematical solutions are built in the first place. When it comes time to deploy, the structural logic for these regularized regressors is detailed in Chapter 7 of 50 Algorithms Every Programmer Should Know. For more visual breakdowns of the core algorithms driving modern data science, head over to the website. True regularization is the discipline of making a model simpler than it naturally wants to be. By mastering the leash, you ensure your algorithm stops memorizing the past and starts predicting the future.